All right, so let's say you have a mixture of a strong acid with a weak acid. Okay, the general rule is, survival of the weakest and non-survival of the strongest. And deal with the consequence of the large Ka first always. That's a good thing to go with, okay? Whichever one is going to be the most reactive thing, deal with that first. So if you've got HCl and acetic acid, or this could be HNO3 or any strong acid, deal with what the strong acid does first. All right? Now, since that's very large Ka, we don't have to do any equilibrium calculations for hydrochloric acid. If it's a 0.20 molar hydrochloric acid, we know the H plus concentration is 0.20 molar. That also, by the way, is going to tell us the pH. So notice, I'm ignoring the weak acid. And the reason why is the K of the weak acid is going to provide maybe 1/10,000th of the hydronium concentration. And these numbers here have 2 sig figs in them, okay? There's no way that the weak acid is going to impact the pH. So for this particular question, I'm literally just going to take the negative log of the 0.20, and that will give me the pH. So if I negative log this, I get a pH of 0.69. Now, the only other question they can kind of ask you is, okay, what will be the concentration of the other ions? And now what we have here is really a common ion problem. Because while we have, and what I've written out here is the equation for the ionization of acetic acid vinegar. And what you can see is you have your weak acid here reacting with your weaker base. So we're going to add a small amount of H3O pluses and a small amount of acetate ions. We're going to assume that we start off with 0.10 molar vinegar, and we're going to write in the 0.2, and the 0.2 will come right from over here. By the way, these could be additive volume questions. If there was like a situation where they gave you volumes, you'd have to do the MV thing first to figure out what the molarities were at the new volumes. Really important point to bring up here. All right. Again, I'm going to ignore the water like I usually do. I'm going to start this one at 0, and we're going to assume now that's going to cause a shift. Now realize what that means, right? If we add more water, it always shifts this thing to the right. So if I were to add more water, we go this way, right? But in this case, I've added more of this, and that essentially shifts it to the left. So we're going to have less ionization of the acetic acid. It already doesn't ionize very much. So while we're going to say that this is going to go down by X, and this is going to go up by X, those changes are going to end up being insignificant. So this is going to be 0.10 minus X, because some of it is going to form. We can't have 0 of the acetate at equilibrium. So we know it's going to shift to the right. Right? So we don't have to do a QK situation here. Make sure you're aware why we don't have to do Q and K. If there's 0 of something, we know it's going to shift in that direction. So it's going to shift to the right, which means we know the left side's going down, and the right side is going up. Okay, so we know this is also going to go up by X. And so in our final equilibrium row, we have 0.20 plus X, and we just have X over here. Now the math here is going to be really easy, because we're going to assume that the changes in concentration due to the weak acid are going to be insignificant compared to the concentration. So we're going to stick with the usual assumption we usually make for the weak acid, that the minus X is insignificant. But we can also assume that this plus X is also insignificant, because 0.20, we're going to see our change is going to be like 0.000 something. 0.000 something added to 0.20. Now, it does happen. There is a change. So make sure you're clear on that, because I've seen AP questions where they brought that up. Okay? It's mathematically insignificant, but it does actually happen. It doesn't really affect the calculation, however. All right. So what do we have in the end here? Let me write this down. So I'm going to write it out over here because I'm running out of space, but I want to see it. So we have 1.8 times 10 to the minus 5, and then we've got, now again, it's approximately equal, so I'm not going to write that because I'm short on space. So I'll do the substitutions in now. So on the top here we have the 0.20, that's our that's our H3O plus. We have X, and the bottom here we have 0.10. And we do the calculations for this. I'm going to rewrite on the other side here. So you have 1.8 times 10 to the minus 5 equals X times 0.20 over 0.10. And make sure that this is our H plus and this is our HA. And yes, we're making an approximation here. When we solve this, we get X is equal to, okay, 0.0000 0.0090. That's a small number. It's basically half of 1.8 times 10 to the minus 5. And that's how you should kind of view this, because you're multiplying by 0.1, dividing by 0.2, so you're really just dividing by 2, or 1/2 that number. And this x, so if we even check the percent ionization, it's like 0.000090 over 0.1. I'm not going to bother with the math. That's definitely a lot less than 5%. So we can assume that's a good assumption. And adding or subtracting this amount to anything is pretty meaningless. And this, of course, is the concentration of the acetate ion. So they can't ask you the acetate ion's concentration, but make sure we're clear. The weaker of the two acids, unless the Ka values are pretty darn close, is usually not going to have an impact on the pH. Okay? That doesn't mean it doesn't cause a shift to the right or to the left, depending on the situation. The shift, however, leads to a insignificant change unless you're talking about a species that starts at 0.